Hi everyone, welcome to part 2 of chapter 13 on solutions. Today we are going to go about talking about how solutions are formed, the type of interactions that are there, and then how we talk about solubility. So the first one is in solution formation. That's what we're talking about first. And there's 3 different types of interactions that go into forming the solution. One of them is the solvent-solvent interactions. In order to form our solution, we're going to need to break some of those solvent-solvent interactions to make room for our solutes. Similarly, we will have to, break or decrease some of those solute-solute interactions to allow it to be dissolved into the solvent. And then our other type of interaction will be solvent-solute interactions. How does our solvent, usually a liquid, interact with our solid, which is, our solute, or our, gases can sometimes be solutes. So how are those interacting? Is that a favorable interaction or not? So, first step. The first step, we have to expand our solute. So our solute, let's just say it's sodium chloride. We're going to dissolve, for this whole thing, let's say we're dissolving sodium chloride in water. And so we would have to expand the solute. We know that the sodium chloride is held together through ionic bonds. Those are very strong, and so it takes quite a bit of energy to kind of spread those out, right? That positive sodium is really attracted to the negative chlorine, so we're going to need to put in a lot of energy in order to kind of spread those atoms apart. So this step is usually endothermic. We're going to have to put in a good amount of energy to expand our solute particles. So here, going from a really ordered system to a more disordered system with the space in between is going to be a positive delta H, right? So it's going to be greater than 0. So we have to put in enough energy to overcome those solute-solute attractions. Our next step will be expanding the solvent. So this is really similar, right? Those solvent particles, let's say water, are held together by hydrogen bonds, which are really strong. So in order to make room for our solute, we need to expand our solvent. We need to make, pull them farther apart, make room for our solute. And so we have to overcome some of these attractions. So this is usually an endothermic process. We have to input energy because, we need to expand, right? Decrease those interactions. So again, this is usually going to be a positive delta H. We need to take our solvent molecules, move them farther apart, and to do that, we need to add energy. And then this last step, step 3, is when we're finally going to mix them together. So we have our expanded solvent, our expanded solute, and now we're going to mix them together. And usually if we're forming a solution, we've picked an appropriate solvent, one that's got, follows the like dissolve like rule. And so this, your solvent and your solute should be attracted to each other through hydrogen bonds or dipole-dipole interactions, maybe London dispersion forces if it's nonpolar. And since they are attracted to each other, usually energy is released when we mix these two particles, or two substances together. So this step is usually exothermic. This is a favorable interaction, so we're going to get a negative delta H. So we're forming solute-solvent interactions. This releases energy, and this is exothermic. So if we combine all of these steps together, the delta H for expanding our solute, and like we said, this is usually a positive value. Delta H for expanding our solvent, and again, this is usually a positive value. And then our delta H for our mixing, that's usually a negative value, right? The first 2 are endothermic, and the last one is exothermic. And if we add them all together, then we will get our delta H for the solution. And we will figure out whether this is going to be exothermic, right? Will energy be released overall, or an endothermic, and energy might be absorbed. Most times, not always, but most times if we have a positive delta H, then our solution may not happen. If we have a negative delta H, though, then our solution will form, right? And it will dissolve. So these values we can use to predict whether our solution will happen, whether we can actually dissolve our solute and our solvent, or we can't. So we can actually predict, right, mathematically, whether this, like dissolves like rule will be followed. Again, like I said in the last set of slides, do not ever say like dissolves like on a quiz or a test. That won't get you any points, but like I said, keep it in your head. It's helpful, right? So if both things are polar, right? If our solute and our solvent are both polar, then we are going to have a very large delta H of our solute because those dipole-dipole interactions are very strong. Same thing with our solvent, right? We'll have a very large delta H for our solvent because, again, the dipole-dipole interactions are really strong. When we mix them, because they're both polar, right, they should have a fairly large enthalpy of mixing. They should be attracted to each other because they're both polar, so we will have a large negative delta H for that step. And then, based on, which one is larger, right, where our delta H1 and 2, were those larger than our delta H3, we can figure out our delta H of our solution, and typically here, the solution will form. If we have, two things that are polar, we can mix them together, and our solution will typically form. If we have something, a solute that is polar and a solvent that is nonpolar, our delta H for our solute, again, will be really large because it's being held together by dipole-dipole attraction, so spreading those out will take a lot of energy. Whereas with the nonpolar solvent, they're only held together by London dispersion forces. So it takes less energy to kind of spread out our solvent because those attractions aren't as strong. When we mix them together, our polar solute is not going to be very attracted to our polar solvent. So it's likely, right, that's why this says small. There's not very much attraction between the solute and the solvent. So this last one, the one that normally, helps us make the solution, is going to be very, very small. So whether it's positive or negative isn't really going to make a difference because we have so much positive value going on. This is going to end up being a very large positive number, our delta H of the solution, which means it took way more energy to separate our particles than we are getting out from the solution, actually being formed. So no solution would form in this case because our delta H of our solution is just too large. Usually for a solution to form, we are looking for a negative delta H value. A very large positive delta H value means it is not thermodynamically favorable. If we have our solute and our solvent are both nonpolar, then it doesn't take very much energy to separate them, right? Because they're London dispersion, they're held together by London dispersion forces. So we can put in a little bit of energy, expand our solute, expand our solvent. And then when they mix together, they're, it's going to be a negative value because they'll be attracted to each other through that London dispersion forces. But it's not going to be very big because, again, London dispersion forces. So it's likely, this will be fairly small, whether it's positive or negative, but the solution will form. Because like dissolves like, right? We're getting out probably a fairly small negative number here. And then in the last one, nonpolar and polar, putting in a little bit of energy to break those London dispersion forces, a lot of energy to decrease those dipole-dipole interactions. But when we mix nonpolar and polar, they are not going to mix well, right? They're not going to be attracted. So we're getting a very small value, right? Because they're not really attracted to each other. So we've got a small positive and a very large positive and a very small, maybe negative number. Gets us a very large positive number, which means our solution will not form. So nonpolar, yep. Polar, yep. So as long as it's like dissolves like, right, mathematically it's going to work out that our solution will form. If we have, polar, nonpolar, or nonpolar, polar, then our solution will not form because mathematically the math isn't just going to work out. It's going to have too large of a positive delta H value. We'd have to put in way too much energy to cause this to dissolve. Maybe we could get it to go by heating it up. Maybe, but it looks unlikely. So here's what it looks like. So here we have our negative delta H. This would be our exothermic, right? So this would be our favorable interactions. This is solutions that will form. And then over here, this is our endothermic side. And most times endothermics will not form. Sometimes they will, and we're going to talk about that in a minute. I'm going to put maybe here. And that one, it kind of depends. But if it's exothermic, then you're definitely going to get a solution that's forming. So we have solute, solvent. We have to input energy, right, to expand our solvent. We need to input energy to expand our solute. And then we'll get some energy out. And the amount of energy that we are getting out really dictates whether or not our solution will form. Here, we didn't get out enough energy to make it worth our while, right? We had to put in a ton of energy, didn't get a ton out, so our delta H of our solution is positive. Which is why our solution will likely not form. But on the exothermic side, we put in, some energy to expand our solvent, some more energy to expand our solute, got out a ton of energy. This would be really strong attractions between our solute and our solvent. So we got out more energy than we put in. So this would be our favorable heat of reaction, right? That'd be our negative value, which means the solution will form. All right, so heat of solution, that heat energy, right? This is our delta H value that I keep talking about, is the amount of energy that's being absorbed, right? Which means it's endothermic, so a positive value, or released, which is exothermic, our negative value, when a specific amount of solute dissolves in a solvent. So here's some substances. We have, and these are all ionic compounds. So the ones that are negative, right, those will dissolve quite well. Sodium hydroxide, we know we have solutions of sodium hydroxide we work with in lab. Hydrochloric acid, same. But these two, right, these are positive values. And based on what we've talked about thus far, we would then maybe predict that these wouldn't dissolve. But they do dissolve. So, what's happening there? Okay. So when some compounds like sodium hydroxide dissolve in water, a lot of heat gets released. The container gets super hot, right? This is a negative value. Same thing here. This is a negative value. And when we put those in water, a lot of energy is being released, like we just showed in those pictures. And the container gets really hot. And a lot of times, just from a practical standpoint, when we do this, you might want to have it in an ice bath. Like if you try and dissolve a lot of sodium hydroxide in water and you're shaking the beaker, the container, whatever it is by hand, it's going to get really hot and it's going to burn your hand. It's really hot. So this would be very exothermic. It's a very favorable interaction. Sodium hydroxide is sure, let's dissolve, let's go. But other compounds like ammonium nitrate, they dissolve in water and it gets cold, which is crazy. But that's because it's endothermic. So you put some sodium nitrate in water, you stir it around, and your solution gets really, really cold. It's going to cool down your hands a lot. And again, that's because we're seeing these positive values, right? These will cause our solutions to get cold. That's endothermic. They are absorbing heat from the water in order to try and, dissolve. So the water gets really, really cold because it's lost energy. So here's what's happening. So in sodium hydroxide, there are really strong interactions between the ions and the water, right? That's that ion-dipole interaction. And a lot more energy is released during the mixing than was needed to separate those solute and the solvent particles. So we're getting out a lot of energy, which is all being released to the water, right? Which makes the water really hot and makes you not want to hold on to the container anymore. Ammonium nitrate, we have some heat being generated when the ammonium and the nitrate ions are interacting with the water molecules, which is great. That's helping us make the solution. But that energy that's being released is way less than was required for the water molecules to break those bonds, right? In order for the water molecules to spread apart, for the ionic bonds to break apart. And so we had to put in way more energy than we're getting out. So that, excess energy has to come from somewhere. So it's absorbing it from the water and cooling our solution down. So this is really endothermic, which makes the water super cold. And just as a side note, for this reason, ammonium nitrate is used in cold packs, which is cool. So if you got hurt, playing sports, they might use an ammonium nitrate cold pack, which makes these, this solution and gets really cold, which is snazzy. So if we have, so why does that solution form at all, right? It has a positive delta H value. It shouldn't form. It's not endothermically favorable. So there's a couple things that favor this whole solution process. One of them is a negative value for delta H. If you have a negative delta H of your solution, then you're getting out a ton of energy by dissolving this stuff, and so that is thermodynamically favorable. We like when things are, negative delta H. And so the other one is the increase in entropy. And I talked a little bit about entropy in our last set of slides, but entropy we can kind of think of as disorder, okay? It's similar. So an increase in entropy is an increase in disorder. And so what I was talking about last time was that, the tendency of the universe, right? This is one of our laws of thermodynamics. The universe is tending towards an increase in entropy. That is what's kind of thermodynamically favorable. And the example I used last time is like your bedroom or, I don't know, somewhere else, your kitchen maybe. If you don't input energy to wash the dishes or put away your clothes or put away your books, fold your laundry, things like that, right? It's much easier to just toss it all on the ground, toss it on the counter, whatever you got to do. That's faster, right? We have an increase in, a tendency towards disordered states, and we have to input energy to go and order it again, to fold our laundry, to wash the dishes, things like that. So this increase in entropy, as it applies to this particular scenario, though, is that by dissolving our solid in the liquid, instead of being that really, really ordered structure, right, where we've got like positive, negative, they're all kind of ordered. When we put it in water, those solid particles now become really disordered, right? They're allowed to break apart and kind of wander about, right? They can zoom around in the water now. That is an increase in disorder, an increase in entropy. So these are our two factors, right? We're looking at the delta H of the solution, but we're also looking at this increase in entropy. So if our delta H of the solution is positive, right, it's endothermic, but we're going to get a large increase in entropy, then sometimes that's enough that the solution will form. So that's what this third one is saying. For positive values of delta H of the solution, the increase in entropy, the increase in disorder, that the fact that those solute particles can dissolve in the water and kind of float away, right, and become less ordered, it outweighs that increase in energy that we needed to input, right? That energy that was, lacking, and can cause the solution process to occur. So this is like for that last example, that ammonium nitrate, right? Even though it had a positive delta H value, it still made the solution because of this increase in entropy. So those are the factors that can happen. And a lot of times this will happen for ionic compounds if it was going to have a positive delta H value. Most ionic compounds, and we learned this when we talked about solubility, right? Most ionic compounds dissolve in water. And the ones that, wouldn't sometimes, maybe with this positive delta H, may with this increase in entropy. So here's how the ionic solids dissolve in water. We've talked about this a little bit before. But, solids... ionic solids, like say this is sodium chloride, will have alternating positive and negative cations. And what happens is that, the positive, or we'll talk about this negative here. This negative, right, like chlorine, is attracted to the water because water has these dipoles, right? They have the partial positive parts and the partial negative parts. So the negative chloride is attracted to the partial positive hydrogens, and the positive sodium over here is attracted to the partial negative oxygens. And so the water can actually go and pull, these pieces of the ionic solids apart because of these attractions, right? So this is ion dipole attractions, where we have an ion like sodium or chlorine, right? Sodium or chloride, that's attracted to something that's polar like water. And then eventually, once it pulls it off, it will then surround these these ions with water molecules, because there's usually a ton more water molecules than they are any of these ions. So ions have been pulled from the main crystal structure by water's polarity, right? And then they are surrounded by the water and are considered dissolved. So here's kind of at a larger scale. We put some salt in some water, right? And this is just kind of looking at it differently with the Mickey Mouse ears. We've got, like this water molecule is orienting itself so that the partially positive hydrogens can pull off that negative chlorine. And as it, pulls them off, eventually it will surround it and we call that hydrated, right? It's now just, surrounded by water molecules. The same thing can happen with these positive sodium atoms. They'll pull off and then they'll get surrounded by water molecules. And again, hydrated. So this will continue to happen until all of your sodium chloride is eventually dissolved in your water. Right, so when sodium chloride is first added to the water, the sodium and the chlorines begin to dissolve because those water particles are, pulling them apart. As it becomes more concentrated, right, this is called a dynamic equilibrium. So what's happening is that over time, the sodium and the chlorine are getting pulled off, but some of them may actually go back and recrystallize. And so we're having this dissolution and recrystallization. So when we have lots of water, and there's still a lot of undissolved sodium chloride, the rate at which the sodium chloride is dissolving is much higher than the rate at which it's recrystallizing. So it looks like it's just dissolving, but in fact, some is recrystallizing. When they're equal, right, if we have the rate of dissolution, right, is equal to the rate of recrystallization, so the rate at which they're dissolving is equal to the rate at which it's precipitating back out, then we can get this dynamic equilibrium. This will happen if you've put, too much of your solid into your water and it can't all be dissolved. So we have these solubility limits, right? The maximum amount that can be dissolved in a set amount of water. So we have these terms: saturated, unsaturated, and supersaturated. So a solution that has solute and solvent in dynamic equilibrium. So here, if the rate of, the rate at which it's dissolving equals the rate at which it's precipitating, right? You have too much salt in your water, and so your water is not able to dissolve it all. It will reach dynamic equilibrium, and it is saturated. So you'll still have some solid at the bottom. And if you add more solid, it won't dissolve, or, it won't look like it dissolves. It may dissolve in this dynamic equilibrium, but the rate at which it's dissolving is equal to the rate at which it's precipitating, so it looks like it doesn't dissolve. The saturation concentration depends on the temperature. Okay, so how much you can dissolve in a set amount of water depends on the temperature. I'm sure you guys have heard, like, if something's not dissolving well, you might heat it up and then it'll dissolve. That's what this is talking about. And also for gases, will depend on the pressure. And we'll get to more about that soon. And then a solution that has less. So if a solution is holding the maximum amount that it can, the solution is dissolved as much as it possibly can, then we call it saturated. If it's dissolved less than that amount, then we call it unsaturated. And if you add more solid, then it will dissolve at that particular temperature. If we have a solution that has more dissolved solute than the saturation concentration, if you've somehow managed to manipulate your solution into holding more solute at a given temperature than it's supposed to, then we call that supersaturated. And this is kind of a special condition. It's hard to have that happen. Usually what happens is we'll heat it up so it dissolves a lot more and cool it down really, really slowly and not bump it, and try and be really careful. Don't talk too loud around the solution, right? And then that's how you can get it to be super saturated. If you've ever made rock candy, the way that you make rock candy, and you can do this at home, is you make a super saturated solution of sugar, essentially, and then you put in a string and you allow the crystals to form on the string over time. It's actually really cool if you've never done it before. I highly recommend it. It's really fun to do at home. So here's what it looks like. If we have an unsaturated solution, and you add some more solute, it will dissolve. If you have a saturated solution, then it's holding the maximum amount that you can. And any additional solid that you add will just fall to the bottom and sit there. It won't dissolve, right? Or it'll dissolve and recrystallize and dissolve and recrystallize, right? But it'll look like no more dissolves. And then if you have a supersaturated solution, you can form, if you have a supersaturated solution and then you try and add some crystals, you try and add some more of your solid, right? You'll get these really weird, unstable crystals that happen, which looks really cool. right? And so that's one way you can tell if something is super saturated. But I actually have a video for you to watch on super saturated solutions in just a minute. So this would be, this just shows you kind of picture-wise. A super saturated solution looks just the same as water, right? This is a homogeneous mixture, and it's got something dissolved in it, but it's holding more than it usually can. And if you touch the surface of the liquid or you add a little crystal, it looks like they're doing, then you'll get these weird, spiky, unstable crystals, and they'll happen really fast, and they'll spread throughout, and they'll make the whole thing into a solid. It is super cool. So I have a video for you. Maybe, will it pause? Will it play in this? Oh, nope, but I will post the link, okay? It's a fun little video. It's like 2 or 3 minutes long to show you just kind of how, chemists play with super saturated solutions. It's really neat. Okay, back to talking about solubility. So for solids and liquids, as you increase the temperature, typically the solid will become more soluble. So as you increase the temperature, you're usually able to dissolve more of your solid. Not always, you'll see this on the graph, but as a general rule, as you increase the temperature, solubility typically goes up. This is like 8% of the time, we'll say. So that's kind of a general rule. For gases in liquid, though, the effect is the opposite. And whenever we talk about dissolved gases in a liquid, I want you to think about how you want your soda. Okay, you want, if you were going to go buy a soda, you would want it to be sealed, right? You would want it to have the lid on, and you would want it to be cold, right? The reason you don't want hot soda is because your soda will go flat, right? Well, and it doesn't taste very good, but your soda will be flat because as you increase the temperature, your gas solubility goes down. Gases only dissolve in cold liquids. As you increase the temperature, those gases will get more and more energy and they will leave. So you want cold liquids, and you want high pressures. And this is, again, you want your soda to be, sealed. You want it to, go tss when you open it, right? When you have that high pressure, your gases stay dissolved in your liquid. As soon as you decrease the pressure above the liquid, right? We call that the headspace. The pressure, like if we have a soda, right? Say that this is our water or our soda down here, right? And there's some area where it's just gas. This is what we call, the headspace a lot of times. And so you want to have a high pressure there to keep your gas in your liquid. As soon as you open your soda, you've decreased the pressure, and that will allow your gases to leave. Okay, so you want a high pressure. You want high pressure and low temperatures. You want a cold soda that is sealed. That is how I would think about solubility of gases in liquids. All right, so back to solids, though, and then we'll talk more about gases in a minute. So solids, like I said, in general, as you are increasing the temperature, most solids will increase their solubility. So just like in general, as we increase the temperature, we're seeing that solubility goes up, which is why most of them have kind of a slope going that way. The only one on this particular graph that goes down would be sodium sulfate. But again, I want you to remember general trends. And so for this case, right, in general, as you increase the temperature, you're increasing the solubility. And we can actually use these curves to figure out if a solution would be saturated, unsaturated, or supersaturated. Because at a given temperature, if it's say like at, 80 degrees. Okay, so at 80 degrees, we could dissolve this amount of potassium chlorate. The line shows you the maximum amount of your solid that can be dissolved at a given temperature. So it looks like, maybe 37 grams of sodium chloride, or potassium chlorate. Maybe 38, who knows. But the line tells you the maximum amount that you can dissolve. If it falls below the line, if an amount falls below the line for that particular compound, then we would call that unsaturated. And if we fall above the line, then we would call that supersaturated. So I'll do this first one for you, and then I want you to try and pause and see if you can figure the rest out. So 50 grams of potassium nitrate in 100 grams of water. These are all in 100 grams of water, by the way. That's typically how we report solubility. We report it as an amount of our solid that can be dissolved in 100 grams of water. And this says at 34 degrees Celsius. So we go, okay, 50 grams of our potassium nitrate, right? So we go to our potassium nitrate line, and we go straight down, right? At 34 and 50 grams. It looks like that is falling right on the line, right? 50 grams, 34 degrees Celsius, looks like it's right on the line. So this one is saturated. Again, if it had fallen below that line, it would be unsaturated. And if it fell above that line, we would call that supersaturated. So go ahead and pause here and try the other ones out. All right, answer time. So if we tried to dissolve 50 grams of potassium nitrate at 50 degrees Celsius, so now we've increased the temperature, so now we're here, right? That is falling well under this potassium nitrate line, so that is unsaturated. If we tried, to dissolve 50 grams in 50 grams of water, so look, careful, right? 50 grams of water, which means that would be 100 grams potassium nitrate in 100 grams of water, right? Because this graph is reading as 100 grams in 100 grams of water. So we need to always have 100 grams of water. So we'll double each of these. So we have 100 grams of potassium nitrate. So we have 100 grams of potassium nitrate at 50 degrees Celsius. So 50 degrees is out here. So if we were managing to make that happen, that falls above the potassium nitrate line. So that says supersaturated. Sorry, I wrote over it. And then on the next one, it says 50 grams of sodium sulfate and 200 grams of water. So again, 200 grams of water, we need it to be 100 grams, so we're going to divide that by 2. So we're going to get 25 grams of sodium sulfate in 100 grams of water at 70 degrees Celsius. So we go out to 70, right? And then we find 25, looks like maybe here. And so that, we find our sodium sulfate line, that's way up here. That falls well below that line, so that means that is unsaturated. And then 100 grams of water in 100 grams of sodium sulfate in 150 grams of water. So we need to take, like 2/3 of this. So that means we're going to get about 66 grams or 67 grams of sodium sulfate in 100 grams of water at 50 degrees Celsius. So we go 50 degrees Celsius up to like 66, 67 grams. And that is falling above that sodium sulfate line. So that means that is supersaturated. So that's how you read this graph. Go ahead and try these out. Similar, just worded a little bit differently, asking a little bit different questions. So pause here. Try and figure out the answers to these questions, and then unpause when you're ready to hear the answers. All right, so the first one says, how many grams of ammonia are needed to create a saturated solution at 30 degrees Celsius? So we go 30 degrees Celsius, we find our ammonia line, which is here. Looks like, 41 grams-ish. Okay. The next one, it says, what temperature is needed to create a saturated solution of 70 grams of ammonium chloride? So we find our ammonium chloride line, right? And we wanted 70 grams, so that's going to be way out here. We go straight down. That looks like, what did I do? Oh, sorry. Grams of solute. Oh, I think my answer is just wrong. Sorry about that, guys. Looks like that answer should be 90. Crazy person, who knows? All right, so 90 degrees Celsius for that answer. The next one says a solution is prepared by adding 30 grams of sodium chloride to water at 80 degrees Celsius. Would this solution be unsaturated, saturated, or supersaturated? So we've got 80 degrees Celsius, and we have 30 grams, so that's here. And we are looking at our sodium chloride line. So sodium chloride, that falls below that line. That would mean that is unsaturated. And then the last one says, how many grams of ammonium chloride are needed to make a saturated solution at 50 degrees Celsius? So again, we're going to use our ammonium chloride line, go out to 50 degrees Celsius, which is here, and it asks how many grams of ammonium chloride. Looks like 50 grams. All right. So rate of solvation. So we can actually affect how fast our solute dissolves in our solvent. And most times we're trying to get it to dissolve faster. It's kind of unlikely that you'd want it to dissolve slower, but if you did, you would just do the opposite of all of these things. But if we wanted to increase the rate at which a solid dissolves, we can increase the temperature, because as we saw in these graphs, as you increase the temperature, right, in general, you are increasing the amount of solid that you can dissolve. So you can increase the temperature. You can stir it up, right? And by stirring it up, what happens is you're increasing the solute-solvent interactions. And we want that to happen, right? Because if you think about how we were showing, water dissolving our sodium chloride, if we increase the amount of interactions, we're increasing the speed at which those solvent molecules are able to kind of bump into those solute molecules and dissolve it. You can also crush your solid into really small pieces. This is also another way of saying that is to increase the surface area, right? If I say increase the surface area, I'm talking about just kind of crush it up. And when we crush up the solid into really small pieces, again, that allows more area for those solvent molecules to go and bump into those solute molecules and dissolve them. Okay. Similarly, I didn't talk about it in the first one, but the increase in temperature, right? If your molecules are moving faster, right, they're going to have more collisions. They're going to bump into each other more. And so your solvent molecules will be better able to dissolve your solute molecules. So what I always say is you can, heat it up, stir it up, crush it up. Those are your ways to increase the rate of solvation. Okay, increase the rate at which your solid dissolves. All right, back to talking about gases. Gases, like I was saying before, gases do not dissolve well in, hot liquids. So as you are increasing the temperature, you are decreasing the solubility of your gases. When we, again, think about soda, right, you're going to want to have a very cold liquid, because then it will allow your your solvent or your solute molecules, right, those dissolved gases, to stay in your liquid. As you increase the temperature of your liquid, right, then you're giving your gas particles more energy. And when they have more energy, they are more likely to leave. So we want to have very cold temperatures for our dissolved gases. So here, this is just, pouring, it looks like Coke from a 2-liter. So if you dissolve if you poured cold soda, right, your gas particles are tending to stay in your liquid. But if you pour warm gas particles, then, they have enough energy and they can try and leave. So you want, if you're trying to have a real nice soda, keep it really cold. The other factor, right, is our pressure. We want to have high pressure for our gas particles in order to stay dissolved. We want a large partial pressure of our gas. Okay, so if we increase the pressure, we can cause more of these gas particles to actually go and dissolve into our liquid. Okay, so if we have an equilibrium here, and then we increase the pressure of the headspace, we increase the pressure of the gas, that essentially kind of pushes more of those gas particles down into the liquid and can cause more carbon dioxide to be dissolved. But the opposite is also true. If you took the cap off, right, now you've decreased this pressure. And you've decreased it a lot. Now it's gone to 1 atm, just like the rest of the world, right? And so now your gas particles, they can leave. And so this is trying to establish an equilibrium here. And since, these keep leaving, your gas particles that are dissolved try to keep restoring this equilibrium. So they keep sending more gas particles up into the headspace to try and restore that equilibrium that they had before. But since the top's not on, right, those gas particles keep leaving, and we keep having this process where the equilibrium keeps trying to be restored, The gas keeps bubbling out of solution, but it's never going to reestablish that equilibrium, so the gas just continues to leave and leave and leave until your soda is completely flat, which would be a bummer. And our last slide for today is just looking at the difference in these two gases. Okay, so we have two types of gases here. We have, oxygen, and we have carbon dioxide. So one of them appears to have dissolved much better in water. We have, our carbon dioxide and our oxygen. Carbon dioxide is dissolving way better in water than oxygen is, right? And the reason for this is their Lewis structures, right? Everything always comes back to Lewis structures. And if we draw their Lewis structures, right, even though carbon dioxide is a nonpolar molecule, it has polar bonds. And water, right, we know is a highly polar molecule. And since it has polar bonds in this carbon dioxide, it's able to dissolve better than O2, right, which looks like this. Oxygen, there is nothing polar about O2 whatsoever, right? And water is really polar. So oxygen is not going to dissolve well in water at all. Again, think about like dissolves like. Nothing about oxygen is even remotely similar, other than the fact that they both have oxygen, to the water, right? We have a really non-polar molecule, a really polar molecule. So comparatively, carbon dioxide, even though it has these, it's non-polar, it has polar bonds, so it's able to dissolve better in water than oxygen is. So that's what's happening here. Again, if you had some kind of polar gas, then that would dissolve even better. And that is actually the end of this particular set of slides. That's the end of Chapter 13, Part 2. So go ahead, keep working hard. Send me any questions you have on Chapter 13, and I will see you guys next time.